Hello everybody. Today, instead of a blog, I'm deciding to re-go through a presentation I gave at the lab seminar today. So I presented this to all my colleagues in the lab and they gave me some feedback and asked me some questions, and I figured I'd just go through it again because it's a pretty good summary of what I'm working on right now, and it's a bit of a change up from reading stuff. So, presentation is called Upgrades to T6 to Experimentally Simulate Gas Giant Entry. What that means is basically T6 is the wind tunnel that I work on most of the time, and we're upgrading it to be able to simulate entry into Jupiter, Saturn, Uranus, and Neptune. That's what gas giants are. So, if you read my blog, you would have seen this video already, but I'm going to show it again because I like it a lot, and I think it's a really good summary. This happened in the presentation Tuesday, where it just stopped really awkwardly, but not to worry. I like the video enough that I'll stick with it. So yeah, this is the Galileo space probe, and it's an artist's rendition of what the mission looked like. So this was basically a spacecraft that they sent to Jupiter, and then from the main spacecraft they dropped this thing, which is an atmospheric probe. And what you can see happening here is the probe entering the atmosphere at 47 kilometers a second. And it gets really, really hot, as you can probably imagine. And just how hot it gets is really the question. That's really the subject of my PhD. So you can see here, this is after it's gone through the high heating entry phase. It drops that parachute and then drifts through the atmosphere, and then this thing collects heaps of data about the atmosphere, what's the composition of the stuff there, how fast is the wind going, what's the temperature, and then it sends this stuff back up to the main spacecraft, which is still in orbit, and then that spacecraft sends it all the way back to Earth. And that's the point. That's the whole idea, is to get data about what's going on under the surface. Yeah, I like this video because it's just really cool art style as well. You don't see this much anymore. It's usually just like really complicated computer simulations, but whereas like back in the day, you get a lot of really cool hand-drawn aerospace engineering stuff, and it's often a lot better. So, I am working on something pretty similar, but for the ice giants, and the ice giants are Uranus and Neptune, these two guys. And so in the presentation, it's kind of technical, but it's not too technical. If you're interested in like what I'm actually doing, then it's worth listening to, I suppose. So I'll be talking about the specific stuff that I'm doing, and in terms of like what things are we actually hoping to get out of the tunnel, and the engineering that I'm doing right now. Presentation structure, who cares? It's lame. You'll work it out. So motivation and background is an engineering term for what is the point of this whole presentation? Why should we be interested in what you're doing? And it's usually directed at people who fund you. But it's worthwhile stuff. So the mission is to send a spacecraft to the outer gas planets, like I was talking about, and this is an example of what the spacecraft might look like. Heat shield, and then this is the actual payload, as it's called. This is the science that they're delivering. And they're potentially wanting to do this in the early 2030s, because that would be as a time when all the planets align in a nice way that you can kind of hit them both at once. So T6, the name of the tunnel I work on, the T6 Stalker tunnel, named after a famous hypersonics researcher, Ray Stalker, is the only facility, and facility is a word for wind tunnel, in Europe that's capable of going fast enough. So I mentioned that for Jupiter it's about 47 kilometers a second, but for these ice giants it'll be about 20 kilometers per second. So T6 is the fastest one. It's the only one that can do it in Europe. And what we're hoping to measure is the stagnation point heat flux, which basically means the heat transfer into the vehicle. How hot does it get? And if we know that, then we can design the vehicle. So that's what the mission is. Why would you want to do this? This is a good question. A lot of people ask me this. So why would you want to go? It would cost about $2 billion to do this mission and send a spacecraft out into the outer solar system. And I think, if anyone knows my neighbor Marie, she always asks me these questions like, why would you do that? Why would you spend $2 billion sending a piece of metal out into space to just look at these kind of balls of gas? Well, other than the fact that it's never been done before, planetary scientists think that Neptune and Uranus are really similar to a lot of extrasolar planets. So these are worlds that orbit around other stars than the sun. And they think that by understanding the structure of these two planets, they might be able to infer information about these extrasolar planets, and that would give them information about a lot of extrasolar planets. They have a lot of unusual properties. The magnetosphere is unusual. Another one, kind of like the sort of elevator pitch one, is that there might actually be life on the moons of these planets. So it's not uncommon for the tidal forces of gravity to heat up the cores of these tiny little moons. So it's a tiny moon next to a really big planet, and tidal forces, which is basically the giant planet pulling, so the moon pulls the tide up on the Earth, a couple of meters, but imagine, and the moon's just a tiny little planet, but imagine tiny little moon, but imagine you've got a massive planet like Neptune pulling on a tiny, tiny little moon, so it will squish like this, and that kind of creates friction that can melt water, and it can stay there long term. And people think there might be life on these planets, on these moons. So that's a reason we might want to go as well. So, role of ground testing. This is basically so that's the mission, and that's all well and good, but what is the part that I'm actually working on specifically? This is a little bit of a technical slide, but I'll try and explain it. So, the main thing to understand on this slide is this graph. So, heat flux is basically a way of saying heat transfer, or how hot it gets. So, up on this graph means really hot. And so on this y-axis is heat flux, so how hot does it get? On the x-axis you've got time, and on this other y-axis you've got altitude, but don't worry about that, we're not interested in that. So these 5 curves are for 5 different proposed entry trajectories. So if you can imagine, if this is your planet, you can enter straight down at an angle like that. So, and these 5 are just plotting the different entry angles that you could take. So a shallower entry angle, you don't have to decelerate as fast, essentially. And for that reason, the heat transfer into your vehicle is less. So I actually looked this up. The heat flux, the peak heat flux here is, what's this? 10 times 10 to the 7. So this is 100 megawatts per meter squared. And if you look up the heat flux from the sun on the Earth, it's something like 400 watts per meter squared or something like that. So that's like 1,000,000 times more heat than the sun per area. So it gets really hot, essentially, is the point. It gets really hot, and exactly how hot is not known unless you test it in a wind tunnel. And if you don't know how hot it is, then you can't effectively design a way to protect it. So that's the whole point of ground testing, is to be able to work out how harsh the environment is going to be, so you can design something that will survive. This is a literature review, which is something that you do quite often in academia, which is just saying what other work has been done and what did they find and what can we contribute. It's all rather technical, really. I suppose the thing to note is that Jupiter entry is at 47 kilometers per second, compared with just 22 for Uranus and Neptune. So that's like a way different environment that you'd expect to encounter there. They do experiments on this kind of thing at the University of Queensland, so shout out if you're from Queensland, and at NASA Ames in California. So they're the two sort of main places where they do experiments similar to what we are doing, or planning to. Planned upgrades and tests. This is what I'm actually working on. So I'm designing a lot of stuff. I'm actually not doing that many tests at the moment. We need to make a lot of upgrades to the tunnel T6 in order to get it to do these tests that we want it to do, because 22 kilometers a second is extremely fast, even for T6. So I'm building something called a new tertiary barrel, an expansion nozzle, and all of the hydrogen infrastructure. So we're testing using hydrogen and helium because that's what's in the atmosphere of these planets, and hydrogen is highly explosive, so we need a way to safely do that, and that's what I'm thinking about. So this is a good little image of T6, just context. I'll try and do a really quick job of explaining how it works, although if any of my supervisors are watching, they'll probably be here to correct me. But essentially it consists of three parts, well, four. There's the free piston driver. So this is, you'd fill up, there's a piston at the back, which is just a big heavy piece of metal, and behind that you'd pressurize that with a really high pressure gas up to several atmospheres of pressure. And then in front of that piston you'd fill it with an inert gas like helium, and then when you fire the piston it will compress the helium up to a very, very, very high pressure. And that very, very high pressure would be something, the highest pressure that we work with at the moment is 46 megapascals, which is, so 1 atmosphere is 100 kilopascals. So what's that? About 40 times atmospheric pressure? I might have got that wrong. It's a lot. So it's so high, in fact, that it bursts a steel diaphragm at this primary diaphragm station. So the steel diaphragm is just a thin piece of metal. And then there's really, really high pressure gas, and it bursts this diaphragm, and then this really high pressure gas sends a shock wave into the test gas. So the test gas is a mixture of hydrogen and helium, and it would sit in this tube here. So this gas gets shocked, and then that bursts a secondary diaphragm, and in this next tube that's full of really, really low pressure air. So what basically happens is the test gas gets heated up massively, and then if you heat something up a lot and then expand it, so it's at really, really high pressure and it goes into this really, really low pressure tube, you massively increase the stagnation pressure and stagnation enthalpy, essentially. So you increase the velocity and you massively increase the energy, the overall energy. Then we get something that might be close to what happens to the spaceship, and then we can shoot it through down to the test section here, and that's where you put a model or something. So the model of our spacecraft. So this is what it looks like, and I'm working on stuff that goes down in this final end here. So here's the downstream end. This is where the shock comes from, like that. And then I'm looking at this steel tertiary barrel. So that's what it would look like. And it kind of sits there. It's all a bit technical, but what you find is when you increase the speed more and more and more, the heating that comes from the gas, so the heat transfer into the spacecraft starts to come more from a physical process, the process of radiation rather than convection. And the way to measure radiation is using these spectrometers. So the purpose of designing the barrel is to put windows in it. So radiation is essentially light, or it's electromagnetic radiation. It's the same thing as visible light, but it might be in the infrared spectrum or it might be in the UV spectrum. And to measure those things, you need these spectrometers. And for the spectrometers to be able to measure these things, they need to be able to see in. And so the purpose of designing this thing is basically to have windows in there so you can see. And this is what it would look like. So it weighs about 650 kilos and it's about 2 meters long. And the key feature is this window here. So it's 190 by 10 millimeters. And if you looked in there as the shock passed through during a test, all you'd see would just be a really quick flash. But the spectrometers can take whatever radiation data there is, and then we can work out how hot it might get, essentially. So I'm thinking about this a lot. Barrel. another thing I'm working on is this this expansion nozzle. So we're looking at exactly the same thing. This is the dump tank, the end bit, and this is the test section where we might put a model, and here's our expansion nozzle. And everything upstream is pretty much the same. So this is where the shot comes from, right to left, goes through this expansion nozzle. So the whole point of doing this is the internal diameter, so the bit upstream in the tunnel where the shot goes through is really, really tiny. So it's, well, when I say tiny, I mean it's 96 millimeters, 96.3 millimeters in diameter. So you can't really put a very big model in there, essentially. So probably the largest size model you could put in would be 40 millimeters across. And you imagine the whole point of having a model in there is so you could put like some instrumentation in and measure stuff, but you can't do that really if the size of your probe is 5 millimeters, then it's not going to fit. So the point of the expansion nozzle is to take that core flow of 96 millimeters and expand it out to a large diameter so that it can be used. Now, there are some drawbacks associated with that. If you expand it out, then you lose some of the properties that you want, which one of them is the density length product, but you can get away with it, so I'm told. So that's the purpose of what I'm doing. Oh yeah, and this is what the model might look like. So you have to put these models for these kind of facilities on really big, like bulky, this is called a sting. This is like the model mounting arm. It has to be super bulky because of the forces that are involved in putting one of these things in a tunnel. Yes, this is what it would look like. The really interesting part is this internal nozzle, internal profile, and that needs to have a lot of thought put into it in order to get the right stuff out the end. So yeah, this would be about 100 kilos and about 1.5 meters long, and machined probably out of one piece of aluminium, which is pretty sick. Yeah, so the thing that I'm spending a lot of time thinking about at the moment is when you go from expanding from a small internal diameter to a large internal diameter, how can you preserve the properties in a uniform way? So really, the goal of, if we're testing something in a wind tunnel, we'd like to know that the wind that we're putting over it is a certain speed and it's relatively constant, so that we can control it essentially. And at the outlet plane, so this is where the model would sit maybe, we'd like to know that the properties at the outlet plane, so like the velocity and the Mach number and as much as possible the pressure, are constant. And so what I'm thinking about is doing computer simulations of some internal nozzle profiles like this that we might want to use. And I'm thinking about, is it going to be constant if we run it at this speed? Is it going to be constant if we run it at this speed? What if this happens? What if this happens? And we can pick one that works for a range of speeds and conditions that we might want to use. So I'm spending a lot of time thinking about that at the moment. This is all technical stuff, but I guess the cool thing is, if you look down here, like this is how fast we're going. That's a cool thing to look at. So these are the proposed entry trajectories that we'd like to match, and around 20 kilometers per second, which is super fast, but pretty exciting as well. And yeah, similar stuff here, I suppose. Yeah, so that's really what I'm working on in a nutshell. It's a really brief summary. Things are really gonna start moving quickly in the next month or two. So all those things I was talking about are gonna start getting built, and then we're gonna start doing some testing in around September. So it's exciting stuff, and hopefully by January of next year, I'll have some experiments done and some cool photos. So yeah, that's been this week's blog. You can't ask questions because this is a recording, but you can ask questions if you're still here in the comments, and you can follow my blog, and then you can ask me any questions you want. All right, if you stuck around this long, thanks for watching. Bye.